Good morning, students. LCR series AC circuit. Yes, in last lecture we have discussed about LCR series AC circuit. Okay, where inductor having inductance L, capacitor having capacitance C, and resistor having resistance R. They are connected in series with AC source. Then what is equation of second order equation of charge? Okay, now we have discussed three theories: AC voltage applied to a resistor, AC voltage applied to inductor, and AC voltage applied to capacitor. Now we will apply AC voltage to LCR series. Means inductor, resistor and capacitor, they are connected in series. And yes, similarly we have to obtain equation of current. Okay, see what is method? Yes, for LCR series AC circuit, to find equation of current, to find solution of I, there are two methods. First is Phasor diagram method and second is analytical solution. We will see Phasor diagram method first. Okay, see what is given? Yes, one inductor, capacitor, and here is resistor. They are connected in series along with AC source. Okay, inductance L, capacitance C, resistance R, and here AC source is potential difference V is equal to Vm sin omega t. Okay, so yes, L, C and R, they are connected in series as shown in figure. Yes, here inductor, capacitor and resistor are connected in series with AC voltage V is equal to Vm sin omega t. AC voltage V is equal to Vm sin omega t. Okay, so yes, LCR they are connected in series with AC voltage V is equal to Vm sin omega t. Okay, what we have to find? Yes, we have to find what is equation of current flowing from circuit. So I am assuming let equation of current, that equation of current flowing from circuit is I is equal to Im sin omega t minus t. I is equal to Im sin omega t minus t. Where what is Im? Im is amplitude, or you can say maximum value of current. And what is del? Yes, del is phase difference. Del is phase difference between I and V, that is current and voltage. Clear about this? So yes, Im is amplitude or maximum value of current. Del is phase difference between I and V. Is phase difference between I and V. Now, yes, we have to obtain what is equation of Im and then what is equation of del. Okay. Yes, Phasor diagram method. So now first of all we have to draw phasor. Phasor means vectors for I and V. Yes, LCR they are in series connection. So obviously in series connection current flowing from each element is the same. So yes, current from each element is same. Yes or no? Yes. So therefore I am assuming phasor of current in one direction and let it is fixed. So let phasor of phasor of current, let phasor of current is fixed in one direction. That phasor of current is fixed in one direction. Okay, that phasor of current is fixed in one direction. For example, yes, it is phasor of current. For example, it is phasor of current in this direction. Any doubt? Okay, yes, it is phasor of current. Now we have to draw phasor for potential difference between two ends of inductor, potential difference between two ends of capacitor, and potential difference between two ends of resistor. Yes or no? Yes. If potential difference between two of ends of inductor, VL, potential difference between two ends of capacitor, VC, and potential difference between two ends of resistor is VR. Okay? Okay, so yes, now we have to draw phasors of VR, VL and VC in this figure. In this figure. So yes, now draw phasors of VR, VL and VC. Yes, remember phasor method. What is phasor? It is rotating vector. Yes, three cases. When first only resistive circuit. In only resistive circuit, V and I, they are in same phase. So yes, phasor of V and I, they are in same direction. Phasor of V and I, they are in same direction. So yes, in resistor, V and I, same direction. So if I is in this direction, then yes, phasor of VR is in this direction. Phasor of VR is in this direction. Any doubt? Any doubt? Okay. Now for VL, yes, remember for pure inductive circuit, current lags behind voltage by phase pi by 2. Current lags behind voltage by phase pi by 2. Current lags means voltage is ahead. So yes, VL is here. Here it is VL. Yes, here it is VL. It is pi by 5. Clear about this? Here it is VL. Any doubt? Okay. So yes, for only resistive circuit, for pure resistive circuit, I and V are in same phase. For inductive circuit, yes, we know that current lags behind voltage by phase pi by 2. Okay. For pure capacitive circuit, so yes, for capacitive circuit, we know that current I leads voltage by phase pi by 2. And see, if you remember, for inductor and capacitor, the situation is opposite. Okay. So if VL is in upward direction, then I can say VC is in downward direction. Clear about this? So it is VC. So it is VC. Any doubt? Any doubt? So yes, current in this direction I have assumed. You have to draw phasor of VR, VL and VC. Means these three are vectors. So how to write vector relation? The AC voltage, V is equal to AC voltage, V is equal to, how to write it is VR plus VL plus VC. Clear about this? VR plus VL plus VC. Any doubt? Any doubt? Okay. So yes, V is equal to VR plus VL plus VC. Okay. Now V is equal to vector addition of these three vectors, first, second, and third. So we will add that. Okay. How to add that? See, I am taking one condition. Which condition? See, here it is. Let VL is greater than VC. Let VL is greater than VC. If VL is greater than VC, see, VL and VC, they are in opposite direction. VL and VC, they are in opposite direction. So yes, if VL is greater than VC, then I can say this vector is VL minus VC. This vector is VL minus VC. Clear about this? Yes. This vector is VL minus VC. So yes, I have vector addition of these two vectors. Now remaining two vectors are, first, it is this VR, and second one is this VL minus VC. According to law of parallelogram, parallelogram. Okay, then diagonal passing from the same point gives their resultant. Gives their resultant. Clear about this? Yes, it gives their resultant. Any doubt? So yes, it is resultant V. It is resultant V. Again, we have three voltage phasors. VR, VL, VC. First of all, VL minus VC is in this direction. Then VR and VL minus VC. The resultant is this. Okay, and yes, it is phasor of I and it is phasor of V. So what is angle or what is phase difference between V and I? Yes, it is A. It is A. Clear about this? So it is figure. This figure you have to draw carefully. Okay. Now how to write? AC voltage V is equal to, it is VR plus VL plus VC. Now how to write its magnitude? See here. See here how to write its magnitude. Okay, see how to write its magnitude. AC voltage V is equal to VR plus VL plus VC. Yes or no? Yes. How to write its magnitude? See, its magnitude is V is equal to, see here it is. First vector is VR, another vector is VL minus VC. Angle between them is 90. So remember law of parallelogram. It is under root VR square plus VL minus VC whole square. Clear about this? V is equal to under root VR square plus VL minus VC whole square. Yes, we have three vectors, but we have first of all found resultant of these two vectors. Yes or no? Yes, it is. So V is equal to under root VR square plus VL minus VC whole square. Now, if I am taking V is equal to V maximum, then I can say I is equal to, it is I maximum. Yes or no? Also, potential difference between two ends of resistor, that is VR, is equal to, it is I and R. Potential difference between two ends of inductor, VL, it is I and XL, where XL is inductive reactance. Potential difference between two ends of capacitor, VC, that is I and XC. Means it is I and XC. Yes or no? Yes, it is. Okay, it is I and XC. So VR is equal to IMR, VL, IMXL, and VC, I and XC. Okay, now if I am taking square of this equation on both sides, then I will get it is V square is equal to VR square plus VL minus VC whole square. Any doubt? Okay, now put when V is replaced by Vm square is equal to VR, means it is I n R whole square plus VL means I n XL minus I n XC whole square. Okay, so therefore Vm square is equal to, here it is Im square R square plus Im common and its whole square, so it is Im square. Here it is XL minus XC whole square. Okay, so now this side I can take Im as common, so therefore Vm square is equal to Im square, here it is R square plus XL minus XC whole square. Clear? Okay, now if I make Im square as subject, then Im square is equal to Vm square upon under root R square plus XL minus XC whole square. And if I am taking square root on both sides, then Im is equal to, it is Vm upon under root R square plus XL minus XC whole square. It is equation of Im. It is equation of Im. Clear about this? Yes, it is equation of Im. Any doubt? Okay. Now see, compare first theory, only resistive circuit. Im Vm upon R. Second theory, only inductive. Im is equal to Vm upon XL. Third theory, only capacitor. Im is equal to Vm upon XC. But here Im is equal to Vm upon under root R square plus XL minus XC whole square. What is this? Under root R square plus XL minus XC whole square. See, here here under root r square plus xl minus xc whole square is called effective resistance of LCR series AC circuit and is denoted by impedance. It is called impedance. Impedance Z is equal to under root R square plus XL minus XC whole square. Clear about this? Impedance Z is equal to, it is under root XL minus XC whole square. Okay, impedance Z is equal to under root R square plus XL minus XC whole square. Okay, now from this equation we can obtain three cases. If it is only pure resistive circuit, so pure resistive circuit, XL and XC is equal to 0. Under root R square means it is only R first case. Remember, only resistive circuit. Only inductive circuit, no resistor, no capacitor. So R is 0, XC is 0, XL square and X square also Z is equal to XL. Clear? Okay. Third, only capacitive circuit. So R and XL they are 0. Okay, minus XC whole square. So this Z is equal to only XC. So yes, if you know equation for LCR series AC circuit, you can easily obtain equations for only resistive, only inductive and only capacitive circuit. Clear about this? So yes, IM is equal to Vm upon under root R square plus XL minus XC whole square. But yes, this equation is for if VL is greater than VC, or we can also say XL greater than XC. If we can say this, XL greater than X. Clear about this? Okay. Now, what about phase difference? See, here it is. Okay. Yes. What is value of IM? Yes. IM is equal to, again, it is Vm upon under root R square plus XL minus XC whole square. So you see this value of IM. Now how to find value of D? Same figure. In figure, it is V. That is phase difference between voltage and current. It is VR and it is VL minus VC. So I can write it is VL minus VC. So yes, D, it is its opposite side and it is its adjacent side. Yes or no? Yes or no? So yes, you have to take trigonometric function tan del is equal to, from figure tan del is equal to, it is VL minus VC upon VL. Clear about this? So therefore tan del is equal to, it is VL, again it is IM XL, VC, here it is IM XC divided by VR, it is IM R. IM common and denominator there is also I, so it will cut. So therefore I can write tan del is equal to, it is XL minus XC upon R, and therefore I can write del is equal to tan inverse XL minus XC upon R. Clear about this? Del is equal to tan inverse XL minus XC upon R. And in this circuit and in this AC, this name is above this VR and I. So I can say this name is positive. Then how to write equation of current? See, the equation of current. How to write equation of current? Here it is. How to write equation of current? Yes, equation of current. I is equal to, it is Im sin omega t minus del, where Im is equal to Vm upon under root R square plus XL minus XC whole square, and del is equal to tan inverse XL minus XC upon R. Okay, but it is phase difference and it is equations when XL greater than XC. XL greater than XC, and this del, that is phase difference, it is above, means it is positive, means it is positive. Clear about this? When we have if VL is less than VC, it means XL less than XC. Then how to write such equation? Yes, how to write such equation? IM is equal to, it is VM upon, it is under root R square plus XC minus XL whole square. And del is equal to, it is tan inverse, and del is equal to, it is tan inverse XC minus XL upon R. And yes, it will be in this downward direction, means it will be negative. It will be negative. Clear about this? So yes, it is LCR series AC circuit. Yes, it is LCR series AC circuit. Clear about this? Clear about this? Okay, so yes, it is all about LCR series AC circuit. Now, last one point, that is graph. That is graph. Okay, what is graph of voltage and current? What is graph of voltage and current? How to draw that graph? See, here it is. Yes, we know that V is equal to Vm sin omega t. Its graph, it is like this. Yes or no? Yes. But what is phasor of, what is graph of I? Is current. It is like this. It is like this. Okay? See, there is phase difference. It is called, its value of current is maximum here, and value of voltage is maximum here. So yes, it is called phase difference between them, that is A. Or also from this, you can say there is phase difference between them A. Clear about this? So yes, it is phase difference between voltage and current. This orange is voltage and this yellow one is current. Clear about this? So it is graph of voltage and current versus omega t. Clear? So yes, it is one complete theory, that is LCR series AC circuit. LCR series AC circuit. Clear about this? Okay, first of all, you have to draw this figure, then this phasor diagram, then you have to obtain equation of IN, that is maximum current, and then equation of phase difference. Okay, but we can consider two cases, when XL greater than XC and another when XL is less than XC. Clear about this? So yes, it is one important theory for chapter number 7, that is solution of current or obtain equation of current for LCR series AC circuit with the help of phasor diagram method. With the help of phasor diagram method. Okay. Now we will see some another cases. Okay.